Okay, welcome to note set 6 in our fifth and final unit on A to D converters with a little DAC stuff thrown in at the beginning of the unit. Not only is this the last note set of the unit, it's also the last note set of the entire course. So I don't know if you're just watching this one or you've watched them all. If you've stuck through the whole thing, hopefully you've enjoyed the course as a whole. So we're finishing off with something called oversampling A to Ds, or a very specific type of that called a sigma delta A to D converter. So there's a little bit of that in the DASP book, but I'm mostly basing my discussion on things from this very nice paper. Provides an overview of sigma delta converters. It's in the IEEE Signal Processing magazine. Really nice publication to find out tutorials and overviews of research directions and things like that. All right. Let's review what we saw for just regular ordinary A to D converters, which I'm now calling Nyquist sampled A to D converters. That just means that they're not really running at exactly the Nyquist rate, because you can't really do that. Although in the analyses we'll do here, we'll assume that we have some ideal scenario where we can literally sample at exactly the Nyquist rate, which would be twice the bandwidth. In the real world, you have to put a little extra sampling rate on there to make sure everything works. But it's called Nyquist sampled A to D converters, just for convenience. Here's a picture from that paper that I'm basing this on. We've got an anti-aliasing filter out front. We know what that does. And here's our sampler. That's just grabbing the samples. And here is our additive noise model for the quantizer. So physically there's a quantizer there, but we've seen in the previous couple note sets that we can model that as additive noise. Let's just assume that the conditions are met for that to behave like we want. So let's not worry about whether we need dither or not. Just assume it works perfectly, so that we know that we have a nice flat power spectral density there for our noise. So we know that we can model the output of this y of n as x of n plus this noise. We know that we can find the power of that noise is delta squared over 12, or we can write that delta out explicitly this way so we can see the dependence on the number of bits. So we see that the number of bits sets the power, the noise power, and as the number of bits goes up, the power goes down, which is good. And so this is what we've been talking about. The noise is spread uniformly across the whole Nyquist band, so from minus Fs over 2 up to Fs over 2. So that's the power spectral density that I'm showing here in red. And the blue is showing the signal power spectral density. Whatever it is, I just drew some interesting shape. So we'll assume that the signal bandwidth is FB and that we are approximately at the Nyquist rate, so everything is right there at the edge. Now, we know that if the power of the noise is delta squared over 12 and the width of this is Fs, we know delta squared over 12 has to be equal to the area of this red rectangle. So from that, we can deduce the height, delta squared over 12 divided by Fs, or delta squared over 12 Fs. So now we know what the height of that is. Okay, so now we can find the signal to noise ratio for this. Now, we integrate both of the power spectral densities, and I'm showing them here with respect to the equivalent Hertz variable. We integrate over the entire Nyquist band, integrate each of them. Now, nothing happens up here. There's nothing really that I can do there. it's going to depend on what the shape of the signal is. So whatever the signal's power is, it's there. But down here, we can do some analysis. We're going to be integrating this rectangle. Well, integrating a rectangle is easy. It's just the area of that rectangle. So it's going to be the height times the width. So there's the height times the width of it. The FS's cancel. And hey, no surprise, delta squared, just like we expected. So why didn't I just go right to here? Because I want you to see this idea that we can, if we don't know what the power level is, the total power, but we know what the power spectral density of the noise looks like, we can figure out the power. And we're going to be doing that in other scenarios than what we've just talked about. Okay, so that's what we've been doing. Now we're going to say, hey, what if we run our A to D converter faster than it needs to be run? Now that in the real world may require you to go buy a more expensive A to D converter because faster A to D converters cost more money. So let's assume we've got money to spend and we're hoping to get some return on that money. And we're going to run the FS at much, much faster than 2 times FB. Let's see what that might do for us. Well, the noise power doesn't change because that has nothing to do with the sampling rate. That only has to do with how much quantization error noise is added at each sample. So each sample is quantized the same way, so the noise power is the same. So the power doesn't change. That means the power spectral density of the noise has the same area before, except now it's spread over a wider range. It was spread over the range of the lower sampling rate before. Now my sampling rate is higher. And so here's a nice picture from the paper that I'm basing these notes on. Here's the signal power spectral density. They didn't make a nice little wiggly one like I did. They're just showing it flat. But here is the noise power spectral density. And here's the important thing. This was FS over 2 when we did Nyquist sampling. But now we're way out here. So this thing is spread way out here. So for Nyquist rate sampling, this noise power was here. And it had to have the same area, so it had to be higher. That's the key. We've taken the same area and spread it out wider so that in the area of the signal, it's much lower than it would have been if we did Nyquist rate sampling. So the signal still lies there. So there's no reason why I can't put a filter on here. And now that stuff is all gone. But the signal power is the same. So let's analyze this scenario where we filter out the noise power. So I like to call that trading bandwidth for bits. Now, the bandwidth here is the bandwidth that your A to D converter can handle, the sampling rate that it can run at. So suppose we've got one that can run at a sampling rate higher than 2FB. And now I'm going back to just FS rather than having FS1 and FS2. So FS is just the rate that I'm running it at, and I'm going to run it much higher than the signal says I need. So the quantization noise is white. Its power spectral density is flat over the entire minus FS over 2 to FS over 2 range. But the signal, as we just saw, is in some narrow subband. So I've oversampled the signal. So I can now apply a low pass filter and decimate back down to the rate that I need for the signal. So I digitally filter to that signal subband and I decimate back to near the Nyquist rate. Now, the signal power has not changed, right? I haven't done anything to the signal, assuming I've made this filter nice with a nice pass band tight around the signal and a tight stop band stopping stuff outside that. So nothing has happened, but the noise power has been reduced significantly, right? I got rid of all this stuff out here. So now instead of being this height times this width, the power is this height times that width. Much less noise. And so my signal to noise ratio has been improved. And we had a formula that talked about something called ENOB, effective number of bits. So if I plug in this new higher SNR to the ENOB equation, the effective number of bits will be more than the physical number of bits, assuming I haven't lost too much to things like nonlinearities and jitter and so forth. So let's just do an ideal A to D analysis. So if that's bothering you, think about taking a bunch of integers and averaging them together to get a fractional value. That's kind of what we're doing. This low-pass filter acts like an averaging. And so we're able to, if we take a bunch of measurements and we get a bunch of different integers, so maybe we get 19, 20, 21, 22, and we get a bunch of different versions of those. You average them together and you might get something like 20.23. So somehow we got that extra resolution despite the fact that we could only measure integers. That's kind of what we're doing here. The analogy doesn't quite exactly work, but that's the basic idea. So this is the idea that we're trying to analyze here. And so we get an increased effective number of bits at the expense of needing a faster A to D converter, faster relative to a rate that I could use if I weren't going to try to play this trading bandwidth for bits game. Now, I'm going to, throughout here, often represent the FS as some number times 2FB. So if D is 1, then I'm operating at the Nyquist rate. If D is bigger than 1, then I am oversampling. So we'll keep our eye on that D. And here I'm just looking at a simple downsampling by a factor of D. Looks like maybe I need to focus on D just being an integer, but no, I can make this, if I use a combination of downsampling and upsampling, I can pick some rational number here for D. Still needs to be bigger than 1 to make this work, but doesn't have to be an integer. But many times we'll just focus on that being some sort of integer just because it's a little easier. Now, here's the big question. How much does this actually help us? And is it worth the cost of a faster A to D converter? Well, let's take a look at that. So here's another picture showing that same shape that I started off with, not what the authors of the paper started off with. And now I've got the noise spread between minus DFB up to DFB. So, right, that's the FS is D times 2FB. That's half that. So that's my FS over 2. So now we know that the whole area of that has to be delta squared over 12. This width is 2DFB, so I can put that in there and find what the height of that thing is. Okay, now I'm going to apply a low-pass filter to pass just this part. I'm throwing away all of that noise power out there. So obviously, the faster I sample, the more noise I push out and the less noise I leave in the signal band. So remember that analysis that we did back a few pages? And I said, hey, why didn't I just immediately put this in here? And I said, oh, I needed you to see that series of steps. Let's do that now for this oversampling scenario. So here we are. Here's our analysis. Nothing changes up here. Everything is minus FB to FB. That's the power of the signal. But what happens down here? I take the noise power spectral density, but now I'm only integrating not minus DFB to DFB, only from minus FB to FB. Now I plug in the height of this thing. There's the height right there coming from here. And I plug in the width that I'm now existing over, just 2FB. Well, now the FBs cancel and I get what I had before, except now I have a D down here. That's the idea. And now we see how this factor D affects. That's our oversampling factor. I can now bring that up here, and the stuff that's left is my original SNR. So that's the SNR if I were to do Nyquist sampling. So if I can sample faster by a factor of D, I'm going to increase my SNR by a multiplicative factor of D. Now that's multiplicative in non-dB. We're going to need to look at these in dB versions. So let's convert this into dB, and it's convenient just for this analysis to let D be equal to 2 to the R. So whatever D is, I can pick an R that's appropriate to get that D value. And now if I take 10 log 10 of 2R times SNR Nyquist, I get this. And I've just added a dB here to say that this is the Nyquist rate in dB. And I see that I've done a little mislabeling here, so that these should be the same for that. What's new? I have a new term out here. Now let's interpret this. This means that I get 3 dB for every integer increase of R. Every integer increase of R doubles D. So for every doubling of Fs, I gain 3 dB of SNR. Now, that sounds like a good thing, and it is. It obviously is making things better, but that's a little bit of a bad trade. So let's think about how that trade compares to actually physically adding a bit. Remember, for this SNR quantization or SNR Nyquist, whichever I call it, in dB, I had 6.02B plus C. Remember that C depended on the level of the signal and also its crest factor. But I still get 6 dB per bit. But now, since that's 6 dB per bit, this gain looks like 3 versus 6. That's what I would get for half a bit. So a doubling of Fs corresponds to just adding a half a bit to my effective number of bits. Not a very good gain. Every doubling of Fs gains me just a half bit of performance. So my claim is that's not a good trade-off. Let's look at an example to see why that might not be such a good trade-off. So let's look at a full-scale sine wave in the audio range. And let's say that we're aiming for CD quality, so 16 bits effective. And so we know that would be an SNR of 98 dB, 98.08 dB. Now let's suppose that instead of doing 16 bits, we are going to use an 8-bit A to D converter, but we're going to sample faster to try to get up to the equivalent of an actual 16-bit. So that's the idea. Instead of using a 16-bit A to D at the Nyquist rate, we're going to try to use an 8-bit A to D converter at a faster rate. And we're going to see how fast do I have to go to get up to 16-bit performance from an 8-bit actual A to D. So let's do the analysis. Here's the formula we just came up with. So that we have from before, and there's the term that accounts for the extra sampling rate, the faster sampling rate. Well, I want 98 dB, so I plug that in here. So there that goes in there. I want an 8-bit A to D, so I plug that in there. And now I need to find out what my R factor is. So now just solve for R, which I did here. Turns out to be 16. And now what is my sampling rate? Remember, it's the D here is 2 to the R. So 2 to the R times 2 times 20,000. We're assuming 20,000 is our band edge, our FB for the audio. That's 2.6 gigahertz. That's a really, 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 really fast A to D converter. Can you buy an 8-bit that runs at 2.6 gigahertz? Yeah, I think you can. It's going to cost a fair amount of money. So you're probably better off just buying a 16-bit running at the Nyquist rate, 44,100 hertz. So that's excessive. So can we do better? Yes, we can do better, and that's where these things called sigma delta A to D converters come into play. So here's the idea behind these things. We are going to use a very high oversampling rate. Now, I thought I just said that that wasn't such a good idea. Well, hold on, we'll see why. Here's the catch. We're going to use a very low bit A to D converter, and we're also going to need a DAC as well. But we're going to just make that a 1-bit A to D converter and a 1-bit DAC. And the reason is that it's very easy, read that as cheap, to make a very accurate and fast 1-bit A to D converter and 1-bit DAC. It's basically just a comparator, really. It's just asking, is it above or below this level? Toggle a bit up, toggle a bit down. That's all a 1-bit A to D converter really is doing. That's it. So by accurate, let me back up here. By accurate, I mean a 1-bit A to D can be made very accurate in the sense that we don't have to worry about any effects of nonlinearity. We don't have to worry about, or we have to worry less about jitter. We have to worry less about missing codes. We have to worry about less about all the things that can cause it to be less ideal. So that's what I mean by accurate. We can make a very cost-effective, very accurate 1-bit A to D converter. Now, we're going to also need some filtering and some feedback, and our job is to try to non-uniformly spread the noise in the frequency domain. So we saw that the noise was spread uniformly over minus Fs over 2 to Fs over 2, and the signal was in here somewhere. But what if we could push most of that out there? That would be better. So that's what we're going to try to do. And here's the system through which we're going to do that. This is modeled after a figure in that diagram, or in that paper. So we've got our anti-aliasing filter out front. Now I should say that that should filter still just to the frequency band of the signal, because we don't want any extra stuff of the signal coming in, although we can tidy it up over here as well. Then we have a transfer function, and I show it as an n-bit pair, but it's usually just 1-bit. Although some people have been experimenting and maybe even bringing to market these days, maybe 2 or 3-bit sigma deltas. It's been a while since I've looked at what's available, because it's been a while since I've had to worry about actually building real-world systems. But most sigma deltas, this n value here is 1. So we have the A to D converter, and then that goes back into a DAC, and then back into the discrete time filter with this feedback loop. Meanwhile, this goes on to the filter and decimate, where I bring the rate down from DFS down to just FS. So we'll assume here that that FS is the Nyquist rate. And here's the idea. Whatever I have here, n bits, this is effectively n plus m bits. So remember, this might be 1 and 1 and 1. So if we can make m be like 15 by doing this, then we will have achieved a good audio A to D converter. And so that's the idea. Now I need to comment on something here. I'm saying an analog discrete time signal and a digital discrete time signal. So all of this stuff, this is based upon bits, binary encoded words. This is binary implemented discrete time signal processing, literally digital signal processing. But out here, this is before the A to D converter and after the DAC. So this is all done in analog. And I'll comment on it again in just a few slides, but it's done with a particular type of capacitor-based technology where the capacitors hold the samples. So there's no quantization, but there is discrete time. So that's the idea. And I'll give a name to that in just a little bit. So here's our goal. Given this structure, our goal is to choose this filter transfer function so that from here to here, the signal has really doesn't get hit by any filtering that will stop it. So it'll have a nice clear pass band all the way through. But the noise that comes in from here, that's the quantization noise, will get attenuated as it goes around this loop. So that's the idea. And analyzing this is not totally straightforward because there is this feedback loop going on here. So we can't just say build that filter to pass the signal and attenuate the noise. No, we'll have to be a little more clever than that. So let's do this. So now look, I can't easily analyze this as it is because I've got mixes of analog things and discrete digital things, and I need a model for my A to D converter. So think about this, right? This path right here, it just goes immediately into the digital world and then back into the analog world. So let's assume that those two things acting as a sequence are virtually perfect so that I can essentially along this path say nothing really happens other than adding the noise of the quantization. So that's what we're going to do to model this, and that's what we've been doing to model this. So I've left off the anti-aliasing filter because we're not interested in that. Here's our H of Z. Here's my model of the A to D converter, and then this feedback path just goes straight back. So the DAC doesn't really do anything, just undoes the binary conversion out of the A to D converter. Now, the noise is still on there, but that's how this thing works. And then this thing goes on, and I'm not analyzing the filter and the decimation. We know how that works. My focus is to try to figure out what I need that to look like and figure out what the spectral densities, power spectral densities look like at the output of this structure before I go into my filter and decimate. So I've got a system here. It's all nice and analog, even though I've got H of Z's in it. So I can model it just with regular H of Z analysis. So There's something called Mason's rule. You may have learned that if you studied feedback systems. You could also just work this out with some algebra and so forth that we've done in the earlier part of the course to find transfer functions. But Mason's rule is the easiest one. I'm not going to go into the details of that, but if you do it, you'll find out that the transfer function from x to y is this. H of z over 1 plus h of z. There's that classic structure that comes from a feedback loop and comes from Mason's rule applied to that. Now, this part is the transfer function from here to the output. Now, it still has to account for the fact that it goes through the feedback loop. So what's feed forward and feedback for this signal is different from what's feed forward and feedback for this path. So feed forward here is 1. Feed forward here is h. But they both have the same loop gain, h of 1 plus h of z. Okay, so that comes from Mason's rule. Now we can say, look, I want this to get over to here untouched. So let's say that's the band of the where the signal stops. So I would like the frequency response of this, which I'm just labeling as gain, to be nice and flat, constant over the signal band. But what I want to happen here is within the signal band, the noise I want to be attenuated. So I'd like this to be, this level to be much lower than this level. So that's the idea. So we've got a signal transfer function and a noise transfer function. And so if we take into account the fact that we're hoping to design h of z so it's effectively a constant there, we'll just make it 1. So say that is just 1 in there, and then this thing will just leave there. So that's the idea. So our job now is to try to figure out how do I pick h of z so that this thing effectively just gives me a 1 there, or at worst, a delay of some sort, which is what we do end up with, as you'll see. Now, here's a figure from the paper that I'm using, and they do talk about sample data discrete time analog signal processing. This is a dividing line. It's not part of the system. It's just showing that to the left of that we have this sample data analog signal processing. To the right of it, we're inside our computer and we have digital signal processing. So the signal comes in, it goes through this h of z, and they're showing you a particular structure that has been determined as being a good choice here. It itself has a feedback loop. We know how to analyze that. Then we're modeling the quantizer with the sum of, or with the addition of the quantization noise. And here's the feedback. We're showing the DAC there, but again, we can just ignore that in our analysis. So since this is a first order filter, this whole thing is called a first order sigma delta modulator. Then it goes into a low pass filter that will pass the signal band and attenuate stuff outside the signal band. So if there's noise out there, and then decimate down by a factor of D. Now, I do want to comment, how do we do this analog discrete time signal processing? It's something called sample data switched capacitor technology. So if you want to know how that works, you can Google that and find out some information about it. There's probably a pointer in that paper to something about that, but maybe not. Okay, so we've analyzed this kind of feedback thing before, so you should be able to do that now and find that its transfer function looks like that. So you can just use standard block diagram rules, do a little bit of algebra analysis, or again, apply Mason's rule, and you'll find that. So now this is what's going to go in here, here, and here, and we can analyze what ends up happening. So if we literally plug this in here and here, we end up with it boiling down just to Z inverse. So it's not quite 1, but it might as well just be. All it does is just delays the signal by 1 sample, and that's perfectly fine. If we plug this into here and analyze it, we get something that looks like this, and we'll analyze that on the next slide. So we see we're not doing anything to the shape of the signal spectrum, so all is good. But we are doing something to the noise power spectral density. What are we doing? Let's take a look. So here's what we had on the previous slide for that H sub E of Z, and I'm just going to convert that into Z form, and I get something that looks like that. I multiply top and bottom by Z, and that gives me that. Well, the reason I did that was so that I could look at a pole zero diagram. I've got a pole at the origin. Yeah, this is an FIR filter, so the only pole I'm going to have is at the origin, so no stability issues, and I have a 0 right here. Now remember, discrete time frequency wraps around like this. So this corresponds to plus and minus pi, or in Hertz, minus Fs over 2 to Fs over 2. This corresponds to 0. So the 0 here is going to give me attenuation at low frequencies. Let's convert this into frequency response. Looks like that. Let's find its magnitude. Expand that using Euler. Now find the magnitude using the rule for magnitude of rectangular form, and you'll get something that looks like that. What does that look like? There it is. I've plotted this versus frequency, but normalized by Fs. So 0.5, that corresponds to Fs over 2. Remember, our Fs is really, really big compared to the Nyquist rate. So that means my signal is probably going to be limited down to this range. That's where my signal is going to live. And you can see this noise transfer function is attenuating the noise a lot in that region. And just I included this level here. That's what I would have for just regular oversampled A to D converter. That half bit per doubling trade-off scheme that we just talked about. Now, this is just the magnitude. Let's look at it in dB. So that's the non-dB plot. Here's the dB plot. We can see that in this range where we would be wanting to suppress the noise power, we're getting things that are minus 10 and more attenuation in that region. So that's good. It's not the best we can do, but that's pretty good, and it'll be better than this. So let's analyze this to see what happens. What is the SNR that we get? Well, we need the power spectral density. So here if we apply these ideas in the time domain, we'll have something like this. We have our x of n minus 1. We'll just call the signal here E sub y of n. So the power spectral density isn't changed at all. You shift a signal back and forth, its power spectral density doesn't change. Power of the signal isn't changed. But the noise power spectral density now is going to be that flat power spectral density modified by the frequency response of that. So remember when we looked at how a random process, wide sense stationary, goes through a linear time invariant system, and we said power spectral density of the input gets hit by magnitude squared of the frequency response to give the output power spectral density. Well, we know that this is going to be flat. So there it is. And we've got the D factor in there bringing the height down. and we're also multiplying it by this. So we need to look at what that thing looks like. Well, there it is. I'm now plotting magnitude squared. So for magnitude squared, it's even lower than what we were looking at with just magnitude. So it's magnitude squared that really affects the power. So that's what we're looking at here. And so this is the thing that we need to integrate over the signal band. So if the signal band is typically here, I need to take this level times these numbers and then integrate that. I'm not going to do that, but somebody did that, and there's a result given in that paper, and it turns out to look like this. So this is the SNR that we would get from the actual number of physical bits in the A to D converter inside the sigma delta. So remember, I was saying that typically that's 1 bit, but you might nowadays have a 2 or 3 bit A to D converter there. Here's the trade-off for that R. Remember, we're, for analysis purposes, looking at the case where we set the oversampling factor D to a power of 2. Doesn't have to be, and R doesn't have to be thought of as an integer in this case. But for every integer change, for every doubling of my sampling rate, I'm now going to get a 9 dB improvement. That's pretty good. But we have to look. Remember, this is our old friend 6 times number of bits plus C, whatever the C is. But there's a penalty that we pay. So the question is, this is just fixed. This is fixed. And now we ramp that up as we say, how far up in sampling rate do we need to go? So if we look at this, though, remember this gave us a 6 dB per bit. This is giving us a 9 dB for every integer increase. Every integer increase in R is a doubling. So that's why we say 9 is like 1.5 bits, right? Because 6 was 1 bit. 3 we said was a half bit gain. 9 is like a 1.5 bit gain. So every doubling of sampling rate with a first order sigma to delta gives us a 1.5 bit gain. That's better than that half bit gain. So that's significant. And again, I just want to comment on this 2x rules because there's a danger to think, oh, my regular A to D converter starts here and then I keep getting this 2x rule, a gain of 9 dB every time I double. That's forgetting this penalty factor. So this 2x rule describes the slope, but not the starting point. The starting point of that line is not the standard SNR quantization level, 6 dB per bit plus C. Nope, it's that amount minus a penalty. Then you start going up. So we'll see more on that in a figure coming up. So if we set R equal to 0, meaning no oversampling, our starting point is not this, it's that minus the penalty. So let's just look at an example here. Set R equal to 0, set B equal to 1, and assume a full-scale sine wave. So now we can put in our 6.02 times 1. The 1 comes from the 1 bit. The 1.76 was what we had for a full-scale sine wave. And then we plug in, we evaluate this penalty with the negative sign out in front. That's minus 5.17 dB. So that's almost undoing all of that. And then since we're at R equal to 0, this term does not contribute, right? We're not doing any oversampling in this scheme. So in that case, we would start out at 2.61 dB. Worse than we would do if we broke the feedback loop and just ran it straight ahead, then we would get 7.78, it looks like. So that's important to keep in mind. But now, as we increase the sampling rate, every time we go up by R equal to a step of 1, we're going to go up 9 dB from that point. So if we go to R equal to 1 from R equal to 0, we'll go from 2.61 up to about 11.64. That's pretty good just for a doubling. And then we'll go up another 9 for the next doubling and so forth. All right, that was a first order sigma delta. Here's a second order sigma delta. And if you want to read this paper, it goes into some more detail as to why it has this particular structure. So it's not quite as simple as I showed before with just a box here with an H of Z and a feedback. There's this extra little intermediate feedback loop as well. But that's what these people who worked on all this in the at the start of this sigma delta ideas worked out. This is a second order sigma delta because it works well and it is easy to figure out. So we've got this discrete time integrator, another discrete time integrator. By the way, that's what was in there before. Notice that there's a slight difference between those two, where those are located. We saw a similar kind of thing when we did our the state variable filter long ago. Notice that when we come back here, we had this structure with the Z inverse here. That gave us avoided the the delay free loop. Now I'll look over here. Back to here. This one has it in the feedback. No delay going through there, but oh, thank goodness we have a delay in the loop. So we avoid the delay-free loop. That's why we do it that way. Now, if you work all this out, you end up with this Z inverse. I think that largely comes from including that in there to avoid the delay-free loops. So that's just like before. But now we had this term here before, but now we have a square of it. That's interesting. Second order is just two of those applied in cascade, essentially. Two of these things applied effectively to the noise. Now we have two zeros at Z equal to 1, and we have even more attenuation at the low frequencies. Remember, our signal is going to be down here. So that's good. And if you work out the signal to noise ratio stuff, you'll get something that looks like this. The penalty has changed a little bit. The trade-off is now 15 dB per doubling. But let's look. We have pi to the fourth over 5. What did we have before? Pi squared over 3. So we pay a higher penalty, but we get a faster payback. So now we get a gain of 15 dB for every doubling, and that's like 2.5 bits for every doubling of FS. That's actually a pretty good trade-off. So let's generalize this to an ELF order. I don't show the sequence of filters inside the A to D converter, the sigma delta. I think the paper might show how that works, but we can just deduce the structure. And it's correct. I'm not really just jumping to conclusions. The paper goes through and establishes that. Nothing different here. Now we have that same term now raised to the ELF power. Now we have L zeros at the or not at the origin, but at Z equal to 1, causing even more attenuation. So I'm showing the first, second, third, and fourth order filters. This is not the squared. The squared is going to be even more impressive, but look, I'd have to zoom in here to see what that fourth order is really doing. It's so far down. It's doing a lot of serious attenuation. And if you analyze this, you come up with, there's our standard SNR for the quantizer. That's the 6 times B plus the constant, whatever it is, 1.76 or such. Here is the penalty. We see the penalty depends on the order of the filter, or the sigma delta. So as the sigma delta order goes up, the penalty gets worse, but the payoff goes up. And so I still have this in the form of something that multiplies the R. And you can check this out. You can plug in the L's that we had for the first order and the second order that we saw explicits, and you'll see that these things match up with that. And we can also include our method that we started off with no feedback. That would just be L equal to 0. That's just oversampling. So you can put that in here and you can see that you'll get the result that we had back then. So now, no surprise, for second order, we gained 2.5 bits. For first order, we gained 1.5 bits. We should get L.5 bits for an Lth order. So L.5 bits for every doubling. Now, there probably are some fundamental practical limitations as to how high of an order you can actually implement in that sample data capacitor technology. Not an expert in that, so I don't really know, but that would be my guess. There's usually limits to these kinds of things. But even just going up to third or fourth order, we're seeing we get a pretty good trade-off for this. And now I'm writing it as per octave, because remember, a doubling of frequency is called an octave. So we often say bits per octave. That just means a doubling of the sampling rate. Let's look at an example to see how this works. For audio, we're aiming for the equivalent of 16 bits. So here is that same formula. I kept this here, I kept this here, but I've just reworked this so that I can see it explicitly in terms of Fs relative to Fb. So instead of putting it in terms of R. But if you were to substitute for Fs, that quantity, see the two Fb's cancel, and you get what we had before, which was what led us to that log 10 of 2R. Okay, so now let's look at our best case scenario, a full case sinus or a full scale sinusoid, and let's assume that our audio band goes out to 20 kilohertz. So we can figure out what our power level is using the number of bits of whatever the A to D converter is inside the sigma delta. So our SNR quantization would be found just by looking at this power divided by this power and taking 10 log 10. Now, the question is, how fast do we need a B-bit sigma delta A to D converter to run at for different orders to achieve CD quality SNRs, 98 dB? That's the question. So I wrote a little MATLAB function where I could put in variables here. So I could put in B values. I could put in a vector with Fs values in it. I could put in F there. That's a frequency range to plot. I can put in all these. I'm sorry. That's FB. That's the band of the audio, and I can put in the order of the filter or of the sigma delta, and I just compute the SNR over a range of FS values. And I plot them. So I did this for an L equal to 0, but B equal to 8. So that was the case we looked at back at the beginning of this note set before we got into sigma delta. And then I did the other two with B equal to 1 for a more classic sigma delta. So this is not really sigma delta, right? That's a 0th order sigma delta. So that's just standard oversampling. So I went back to the 1 bit. So that gives this a little bit of an excessive advantage, but it still does very, very poorly. If I were to switch to 1 bit for that, this thing would be ridiculous. It would be way down here. But so this is a function of the sampling frequency and the SNR that I get. Now, remember we talked about the starting point. There's this quantity and the penalty. So this thing starts, there's no penalty factor for L equal to 0. That goes away, and we start at where we would expect. Plug in the 8 bits, 6 times 8 plus 1.76. That would go in as the starting point, and then we go up with our trade-off. 3 dB per every doubling. For this one, we start with 1 plugged in there, so it's going to be 6 times 1 plus 1.76 minus the penalty. So it starts way down here. And then for L equal to 2, we still, same thing here, 1 times 6 plus 1.76 minus the penalty. Starts down here. But notice that the red one, the L equal to 1, its rate goes up at 9 dB per doubling. Am I right? 9 dB per doubling. And this is going to go up. Wait, did I get that right? I better go back here. Yeah, second order. First order was 9 dB per doubling, and second order was 15 dB per doubling. Okay, so let's go back here. So so I had my 3 starting points. This one goes up at 3 dB per doubling. This one goes up at 9 dB per doubling. This one goes up at 15 dB per doubling. I've drawn a horizontal line at my target 98 dB level. Now let's look to see what I need. The question is, at what sampling rate does each of these 3 methods achieve my target 98 dB? Well, let's look at the just simple oversampling starting with 8 bits. I have to go all the way out here to hit that. We saw that already. That was the 2.6 gigahertz that we saw for that example way back then. Very excessive. How about this one? First order 1-bit A to D converter, 61 megahertz. That's not too bad, actually. For a 1-bit A to D inside the sigma delta, not hard at all to hit 61 megahertz. And what about this one? 4.7 megahertz. Again, piece of cake for a 1-bit A to D converter to be running at that. So that's how these sigma deltas achieve this. And you can go out and buy these things. You don't have to build this. Someone else has built it. But it helps to know how it's working inside and how it's giving you that trade-off. So let's just quickly summarize this, and that will finish out this note set, that will finish out this unit, and that will finish out the whole course. So there's 3 advantages to sigma deltas. Not so much from the point of the user. So the user might not really care whether your audio is using a sigma delta or not. but from somebody who is making the system. They might find some of these trade-offs, and they might impact ability to buy things at certain costs and so forth. So here's the advantages of the sigma delta. So I didn't actually mention this. The oversampling that happens makes the anti-alias filter that you need out in front of this super easy. I had alluded to the fact that the anti-aliasing filter should pass the signal band, but I didn't say anything about the fact that its transition band to the stop band can be very slow. So if this is F, we can have out to FB a nice flat band. Now, if I'm not doing sigma delta or oversampling at all, I need this to come down pretty quickly. But with oversampling, especially the sigma delta, I can let lots of stuff in. Why? That will all get cleaned up with the digital filter in the filter and decimate. So that's good. Again, this is something that's going to be inside the sigma delta chip. So as a purchaser of this, you don't have to necessarily be worried about that design. The noise shaping from that feedback loop inside the sigma delta, its job is to take the same amount of power and spread it out over the larger band that we're sampling at, and push a large portion of the noise power outside the signal band, rather than spread it uniformly like oversampling non-sigma delta did. We're pushing even more noise power outside the signal band. And because of that, we get a high trade-off, and that means we can start with a very low bit A to D, maybe even 1 bit inside the sigma delta, and those things can be made virtually ideally. So those nonlinearities and things like that we mentioned in earlier notes, not an issue. So can be made cheaper. Nice. Disadvantage? Well, you need to run things at higher sampling rates. But we just saw, what did we see, 64 megahertz or 61 megahertz or even 4.7 megahertz? That's not a big deal for a 1-bit A to D converter. So that's not that big of a disadvantage these days. And the complexity and cost of making that chip might be more, because you got to put in the capacitor, switched capacitor technology and so forth. But the advantages far outweigh the disadvantages. Now, is that to say that if you're building an audio system, you must run out and buy a sigma delta A to D converter? No, just one tool in your box. So you need to know about these things so that you can analyze them, do the pros and cons, do the trade-offs, and figure it out and get the best performance for all your requirements and constraints. So that finishes us up. We're done with this slide. We're done with this note set. We're done with this unit. We're done with the course. I hope that you have enjoyed the course and find some interesting things in there. I've had a lot of fun making the course, and now I've put it up online and making it available to anyone who wants to take the time and effort to go through all the stuff.